In 2006, NASA published The Power of 10, Rules for Developing Safety Critical Code. Now the coding constraints are high because the stakes are high. The question I want to explore is, can some of those rules help you as a game developer write better code? So we're going to go through those rules and find out, all right? Keep in mind, this document is also mainly targeting at C. So of course, when you develop game with C# or C++, not everything applies. Still, it's going to be quite interesting, so let's go into it. Most serious software development projects use coding guidelines, and I'm sure you have coding guidelines in your game development project. These guidelines are meant to state what the ground rules are for software to be written, how it would be structured, and which language feature should and should not be used. This is actually a good point, which language feature should and should not be used. Sometimes you see in C#, especially the link system, which is very convenient, but overall very performance hungry and generates a lot of garbage. So, this is the kind of stuff. Curiously, there is little consensus on what a good coding standard is. It's still the case. It is from 2006, 2025 now. It's still the case. Everybody codes as they want, and people lose their mind when something is successful and they see the code base being totally, let's say, against best practices. Among the many that have been written, there are remarkable few patterns to discern, except that each new document tends to be longer than the one before it. The result is that most existing guidelines contain well over 100 rules, sometimes with questionable justifications. Some rules, especially those that try to stipulate the use of white space in programs, may have been introduced by personal preference. True. Others are meant to prevent very specific and unlikely types of error from earlier coding efforts within the same organization. Not surprisingly, the existing coding guidelines tend to have little effect on what developers actually do when they write code. That's true. I'm not sure if coding guidelines are used by the developers actually writing code. It might be like someone higher up in the hierarchy that says, we need to code like this. And then the other developers that anyway do the code, they're like, sure. Not surprisingly, the existing coding guidelines tend to have little effect on what developers actually do when they write code. That's funny. That's actually a based take, I think. It's very close to reality, I think. The most dooming aspect of many of the guidelines is that they rarely allow for comprehensive tool-based compliance checks. Tool-based checks are important since it is often unfeasible to manually review the hundreds of thousands of lines of code that are written for larger languages. Okay, so here we are talking about tools that should enforce some of the guidelines automatically, which is a good thing. The benefit of existing coding guidelines is therefore often small. Even for critical application, a verifiable set of well-chosen coding rules could, however, make critical software components more thoroughly analyzable for properties that go beyond compliance with the set of rules itself. To be effective, too, the set of rules has to be small and must be clear enough that it can easily be understood and remembered. Makes total sense, 10 rules are easy to remember. 20 rules starts to be like complicated, and 100 rules starts to be a bit unserious. You spend more time trying to follow the rules than actually writing your code. The rules will have to be specific enough that they can be checked mechanically to put an easy upper bound on the numbers of rules for an effective guideline. I will argue that we can get significant benefit by restricting to no more than 10 rules. Such a small set, of course, cannot be all-encompassing, but it can give us a foothold to achieve measurable effect on software reliability and verifiability. To support strong checking, the rules are somewhat strict. One might even say draconian. The trade-off, though, should be clear when it really counts, especially in the development of safety-critical code. It may be worth going the extra mile and living within the stricter limit that may be desirable. In return, we should be able to demonstrate more convincingly that critical software will work as intended. So, overall, great introduction. And don't forget, this is for safety critical system, like satellites, probes, or any kind of things that should really not fail at all. Like you cannot get stuck in an infinite loop. You cannot just have random crashes. You cannot have memory leaks and this kind of stuff. So it makes sense that you need some strict rules that doesn't hinder development, but still provides like a clear way to write less bugs. The choice of language for safety critical code is in itself a key consideration, and written in C with a long history, there is extensive tool support for this language, including strong source code analyzers, logic model extractor, metric tools, debuggers, test support tools, and a choice of mature, stable compilers. For this reason, C is also the target of the majority of coding guidelines that have been developed. For fairly pragmatic reasons, then our coding rules primarily target C and attempts to optimize our ability to more thoroughly check the reliability of critical applications written in C. I wonder if NASA still uses like majorly C, or have they explored also other languages like, I don't know, Rust or stuff like that? Would be interesting to see. I'm sure they don't put JavaScript on their satellites. I hope not. So let's start with the 10 rules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's see how it can apply to game development. It might or might not be. Rule number 1, restrict all code to very simple control flow constructs. Do not use go-to statements, set jump, long jump construct, and direct or indirect recursion. Of course, go-to statement, this is low-level programming. We don't, let's say, in the world of game development, if you build with C# or even C++, I don't think you would use those things. However, direct and indirect recursion, that's interesting. So let's see what it means by that. Simpler control flow translates into stronger capabilities for verification and often results in improved clarity. That's true. We've seen in the Command and Conquer code, some code is, let's say, not pretty, but super easy to understand. Like the control flow, so the flow of the code, the easier it is, the less bug you have, even if it's like just longer. That's fine. The banishment of recursion, so we banish recursion, okay, no recursion, is perhaps the biggest surprise here. Without recursion, though, we are guaranteed to have an acyclic function call graph which can be exploited by code analyzers and can directly help to prove that all executions that should be bounded are in fact bounded. Note that this rule does not require that all functions have a single point of return, although this often also implies simplifies control flow. There are enough cases though where an early error return is the simpler solution. So no direct and indirect recursion. I mean, direct recursion is your function calling itself. That would be direct recursion. Indirect recursion, what would this be? Would this be like a function calling another function that is calling maybe another function? And one of those functions at some point calls back one of those functions that initially has been called. So without knowing, you created recursion. So of course in GameDev, if you say no recursion, I'm overall quite in favor of that, simply because I don't spend the time, which is my fault, to actually check that the recursion will stop. So you might implement your algorithm well, but have you tested it really well that it's really stopping? Because recursion is, overall, it's always considered dangerous. Like, of course, there's different dangers or risks about recursion. Do you use recursion to generate your dungeons, your terrain, and so on your computer? Or do you use recursion as a core functionality when you ship the game? So the player is actually running recursive functions on their game when they play it. This type of recursion, I would be like making sure that the recursion has actually a limit, which is easy to do. If a function calls itself, you can still track how many times this function has been called and just have a limit on the def bounds. So you say, okay, I can implement recursion, but I'm going to code strict rules inside it that, well, after, 1,000 recursive calls, normally my terrain generator doesn't need 1,000 recursive calls. So if I reach 1,000, I'm going to stop and assume this is the end and then start to work back the recursion stack. Very interesting. Makes total sense. Recursion is always prone to errors. And many algorithms I think many algorithms can be implemented without recursion as well. Not all, but many. So rule number 2. All loops must have a fixed upper bound. It must be trivially possible for a checking tool to prove statically that the present upper bound on the number of iterations of a loop cannot be exceeded. If the loop bound cannot be proven statically, the rule is considered violated. The absence of recursion and the presence of loop bounds prevents runaway code. This rule does not, of course, apply to iterations that are meant to be non-terminating. For example, a process scheduler. In those special cases, a reverse rule is applied. It should be statically provable that the iteration cannot terminate. Yes, so let's say your game loop. You should be able to prove that your game loop never stops. You don't want your game loop to stop, except when the user says quit. Which is not really, if you are building your engine, this is important. If you are just using, a game engine, then this has been done for you normally. One way to support the rule is to add explicit upper bound to all loops that have a variable number of iterations, code that traverses a linked list, and so on. When the upper bound is exceeded, an assertion failure is triggered and the function containing the failing iteration returns an error. Yeah, so it mentions here the upper bound, an explicit upper bound. That's interesting. So what they mean exactly by a fixed upper bound would be like, so if you would have a collider check, you cast a sphere cast somehow, and this function will return you an unknown number of colliders within that space. So this unknown number of colliders could actually crash your game. If someone, let's say in an kind of an open world game, manages to bring all kinds of objects into one place, and this sphere cast happens then, and your game lags or crashes even, that would be, of course, the player brought this upon himself, but you could actually avoid this. You could avoid this by saying, okay, when I do a sphere cast, I know that I don't know how many objects I have, but I can safely say, well, above 200 colliders, it starts to be unreasonable and not part of the gameplay that you envisioned. So then you can do something else. You ignore those 200 more. And if you say, well, no, I want to really support, 100, 200, 500, any kind of number of objects at a given place, like you build a simulator like Satisfactory or whatever, where the player can really, really use all of his imagination to build really giant stuff, well, then you don't really want to say, no, it's maximum this amount. So you can still have a fixed bound, but maybe your fixed bound is super high. So maybe you go in the thousands or even in the tens of thousands, and you optimize that way. But if your game is smaller and you think that, oh, well, if in this room the player manages to bring, 100 enemies in my room, things are going to break, well, then you can still make, let's say, explicit bounds to say, well, past that number, those other ones will be discarded or ignored or whatever. Not ideal, but it's one way to make sure that you don't encounter crashes or very bad, let's say, limits of your game. It is interesting. It can be done like that. Another thing it can apply to is actually, if I take Unity, for example, you have the alloc version of raycast and the non-alloc version. So the non-alloc version, you have to give a list with a certain amount of slots inside. And that actually really fits this. You can give an array, we say, well, I'm going to do a raycast, and here's an array with 10 slots. And you're always going to get always 10 items maximum in that array. That would be, I think, considered to follow that rule. So it's a good rule, I think, for GameDev. Rule number 3, do not use dynamic memory allocation after initialization. So I think this is more for C, or if you really need to manage your memory yourself. So dynamic memory allocation means that whatever you get at the beginning, you cannot take more than that. Does this mean that? Not sure. So we are forcing all applications to live with a fixed pre-allocated area of memory. A pre-allocated area of memory can eliminate many of these problems and make it easier to verify memory use. I don't think this applies so much to game development, except if you maybe build your own engine. But I would consider this not relevant for game development. But I say a lot of but. The point of before of maybe the alloc versus non-alloc could actually maybe be interesting to that. So you don't allow a dynamically sized array of collision. You just say, well, I'm going to only handle X collisions or X-ray cast results in this place. That would actually kind of be about this rule. So it's not that bad. It's a good rule. There are only 10 rules overall. Rule number 4. No function should be longer than what can be printed on a single sheet of paper in a standard reference format with 1 line per statement and 1 line per declaration. Typically, this means no more than 60 lines of code per function. Are you printing all your source code on paper? I don't, but I have to say, if I would create, let's say, a hugely successful game, I would be inclined to print kind of an archive copy on paper and keep that in my files. That would be actually quite fun because like you build something great and you just have it on a computer, on a Git repo, on some server. Why not print it, you know? Okay, it might be a lot of pages, but actually it would be kind of a fun thing to keep around as a historical document for your solo or your entrepreneurial life. That's actually funny. However, here is not the point. The point is to have small functions with not many lines of code. Each function should be logical, unique in the code that is understandable and verifiable as a unique. It is much harder to understand a logical unit that spans multiple screens on a computer, display or multiple pages when printed. Excessively long functions are often a sign of poorly structured code. He said it. If you write long code, you have poorly structured code. It's written here, black on white. I agree. I like to create small functions that just do one thing. And if I see sometimes some, let's say, update methods that are super long, I like to just split that part into multiple functions. So I would have a function move. I would have a function jump. Even sometimes I call it different. I call it handle move, handle jump, handle input, handle interaction, and so on. And they are just getting called one by one, and they try to not fight each other, you know. So the handle jump just directly decides, oh, am I allowed to jump? Yes or no? Can I jump? Blah, blah, blah. And then we handle the jump. The move is like, okay, should I move? Can I move? Then I will move. It's not like, oh, let's mix all the things in the beginning. Can I move? Can I jump? Can I interact? And then at the end we say, oh, then let's move actually the player finally now. Also, we rotate him. And now we apply the animation. And, oh, but if this is a special case, then I also apply this animation. That starts to be then really long updates function. And splitting them into smaller parts might actually be easier to handle. So I'm a huge believer of small functions. 60 lines is a lot, right? I would be inclined to go smaller for most use cases. For most functions, I go smaller, I think. Rule number 5. The assertion density of the code should average to a minimum of 2 assertions per function. Assertions are used to check for anomalous conditions that should never happen in real-life executions. Assertions must always be side effect free and should be defined as Boolean tests. When an assertion fails, an explicit recovery action must be taken. For example, by returning an error condition to the caller of the function that executes the failing assertion. And any assertion for which a static checking tool can prove that it can never fail or never hold violates those rules. So it is not possible to satisfy the rule by adding unhelpful assert true. Yeah, assert true is not helpful. That's pretty true. Let's read this rationale and then. Statistics for industrial coding efforts indicate that unit tests often find at least one defect per 10 to 100 lines of code written. The odds of intercepting defects increase with assertion density. Use of assertions is often also recommended as part of a strong defensive coding strategy. As part of a strong defensive coding strategy. Okay. Assertions can be used to verify pre- and post conditions of functions, parameter values, return values of functions, and loop invariants. Because assertions are side effect free, in this case, they can be relatively disabled and testing in performance critical code. So a typical example, so if not assert, return error, and the assert is defined like that. So here the assertion is actually a Boolean check, and it returns an error. In most, like if I think the assert in most, let's say, other languages is a hard failure. It's like if the assertion is false, your program stops. It just stops. And actually, assertions I think are underrated, especially for game development, because you tend to go into, how it is saying here, defensive programming, which basically translates to having a lot of null checks and fixing your code with null checks. So you start coding, and at some point, well, your code expects a certain object. Oh, but that object doesn't exist yet, or it has not been initialized fully yet, or this or that. And you are like, oh, I got a null pointer exception at this line. Well, easy to fix. I'm going to do, if it's not null, then I do my code. So you end up with a lot of null checks all around your code, when actually the issue is at the beginning somewhere, where you didn't maybe respect the flow or the life cycle of your objects, which means, for example, in Unity, doing always the same things in awake, doing always the same thing in start, and respecting that order. So you know that once you're in the start, everything that has been done in awake through all the objects are done and ready, this kind of stuff. But if you mix up things, and you mix up where things are happening in the life cycle, you end up with a situation where, well, in one function, you are not sure if you are really get that object. Is it already set or not? And then you put a null check, and that null check works because, well, frame 1, it was null, frame 2, it was not null anymore. And then that way your code works, but you actually put a lot of null checks because the structure of the code behind is actually messy. So assertions allow you to say, well, at this point, you want that this is defined. You want that this is the result. You want that this is the result. And if it is not the case, you crash the program. And I like that. It's like it forces you to fix your program before just trying to fix some causes that really are unrelated. So you need to fix the underlying base, have everything well defined, and with assertions, you can actually do that. And then down the line, after the assertions, well, your code will be much simpler because you know what you have, you know what you get, and you know what you have to return. And those assertions can actually help you to go a bit away from defensive programming. The early failure at the assertions is kind of your early warning that, okay, something is not good in the beginning. You don't need to go fix things and do null checks at the last function that is called down the line. And just to provide a metaphor, like overly defensive coding is like putting a life jacket on a life jacket on a life jacket and just being bloated. Of course, you will not go under, but you obviously have too many life jackets. If you could just spend a week and learn to swim, that would be fine. Then you just need a small light jacket and you will feel much better. That's overly doing defensive programming, in my opinion. Rule number 6. Data objects must be declared at the smallest possible level of scope. Supports the basic principle of data hiding. Clearly, if an object is not in scope, its value cannot be referenced or corrupted, and so on. So I guess this is about, if I would apply this to game development, this would be reduce global state as much as possible and make use of local scoped access of variables as much as possible. So you don't want functions to be able to reach too much of your entire code base, because the more things can reach to other parts of your program, the more there is a chance that somewhere you say, well, I want to really do this because I'm at this place and I need this data to be transformed. Well, how about I just get it and change it? I found that in Unreal Engine, you have a lot of global state and you can reach from code to so many objects very quickly. It's crazy. I think it is crazier than Unity. Unity still, you can also reach to nearly everywhere, but I feel in Unreal Engine it's even more of that concept. You can really reach far and kind of everywhere you can find your way to some data, which gives you flexibility and it gives you kind of an ease of coding. But without some discipline or some rules, you can end up in spaghetti code so quickly, which is not something you want. Rule number 7, the return value of non-void functions must be checked by each calling function, and the validity of parameters must be checked inside each function. So the return value of non-void functions must be checked. If I understand the rule correctly, is like some functions return you things that you purposely ignore, and that would violate that rule. So let's say you do a raycast, and the raycast, well, if it fills an array but also returns you the raycast hit, or maybe it returns you a boolean. So not using that return value in any way would violate this rule. So you are getting something back that you are not checking. But overall, I'm not sure I like this rule so much, because oftentimes you get something back and you know purposely that you don't need it. Some languages actually have an explicit way to say I don't care about that return value. I think in Python you have that, where you can say an underscore, and then that is basically like a slot. The return value will get into it, but you ignore it. But it's an interesting concept. Here was something fun. Standard libraries famously violate this rule with potentially grave consequences. See, for instance, what happened if you accidentally execute string length of 0 or string cat s1 s2 -1 with a standard C library. It is not pretty. Great shitting on the C library. Fun fact, the Unreal Engine doesn't use the standard C++ standard library. And the history for that, as I understood, was that at the time they built Unreal Engine, the C++ library was not stable. So it's a standard library and it was not good. Apparently, they moved too fast to take all the latest fancy tech and methods, and it had more bugs. So they just implemented their own for having full control of what actually goes into the game engine. It's an interesting story. By keeping the rule general, we make sure that exceptions must be justified with mechanical checkers flagging violations. Often it will be easier to comply with a rule than to explain why non-compliance might be acceptable. Again, I mean for NASA, high stakes and high constraints. Rule number 8. The use of preprocessors must be limited to the inclusion of header files and simple macro definition. Token pasting, variable argument lists, ellipses, and recursive macro calls are not allowed. So this is a C thing, right? The macro preprocessors and so on is a C thing. All macros must expand into complete syntactic units. The use of conditional compilation directives is often also dubious, but cannot always be avoided. This means that there should rarely be justification for more than 1 or 2 conditional compilation directives, even in large software development efforts. Beyond the standard boilerplate that avoids multiple inclusion of the same header file, each such use should be flagged by a tool-based checker and justified in the code. So macros, those are like in C, the hash macro, and then you can define a function there. It's very ugly overall. I think everybody agrees that it's ugly. You have in, for example, C# or other thing, the conditional compilation directives, the hash if, hash else, and so on. And even in GameDev, it's not avoidable, but it's super ugly. Let's say if you build a game and you want to ship it on iOS and Android, well, guess what? There are some libraries for Android that you need to include for example, payment or in-app purchases. And for iOS, there are other libraries. And of course, one is not compatible with another one. You cannot ship the Android stuff with the iOS stuff. It simply doesn't work. So you have to use those pragma marks, hash if the device is an iOS device, well, then include those headers, include those imports, and also then you need to conditionally compile certain methods. How would you go about avoiding it? So if you don't want to have conditional compilations, checks, let's say if it is Android, then do this, if it is iOS, do that, you would essentially need to have 2 code bases. In practice, you would not have 2 code bases, you would have 2 branches, iOS branch, Android branch, and implementing both things that. However, this starts to be really annoying because you have your 2 branches And then when you add more gameplay or fix bugs, well, you need to also propagate those things in the iOS branch, the Android branch, Linux branch, Windows branch, I don't know, Steam Deck branch, Nintendo branch, whatever. So maybe, you know, one ugly file with conditional compilations might in this case be easier to manage than, you know, one branch per target device. But yeah, it's not really avoidable. The thing here, the point is just not use C preprocessors. The use of pointers should be restricted. Specifically, no more than one level of dereferencing is allowed. Pointers dereference operations may not be hidden in macro definitions. Just to make sure you really want to use macros, please don't use macros. Or inside type-def declarations, function pointers are not permitted. This is sad. I mean, it makes sense. Pointers are easily misused, even by experienced programmer. I would say especially by experienced programmers, because they're like, oh, pointer of pointer of pointer? Fine. They can make it hard to follow or analyze the flow of data in a program, especially by tool-based static analyzers. Function pointers similarly can seriously restrict the types of checks that can be performed by static analyzers. Yeah, I mean, their point is we cannot really check well without tools, function pointers, so it's not allowed. And should only be used if there is a strong justification for their use, and ideally alternate means are provided to assist tool-based checkers determine flow of control and function call hierarchies. You know, a strict environment and they want to check that the program will behave in a certain way. Function pointers make it difficult to do that. For instance, if function pointers are used, it can become impossible for a tool to prove absence of recursion. Okay, there it is. So alternate guarantees would have to be provided to make up for the loss in analytical capabilities. So you are in for some long writing and talks if you want to use function pointers at NASA. I like function pointers overall, and for what I use them? I use them to basically configure things in a modular way without hard coding it in the code. Like, not necessarily for game development, more like some tools I built for myself or this kind of stuff, where I actually define in a configuration file things, and that configuration file will be used well to call a method. And especially, let's say I like to do that in Python, that I can just pass a function to another function. I will say, well, you do that, and here's a function that you need to call also. The same with classes. Like, I give then a definition of a class to a function, and that function doesn't really know what class it is. It just knows, okay, I will instantiate that class and call something on it. Yeah, it can be crazy to understand and follow, but in some cases, it gives you, let's say, a level of modularity at runtime that would otherwise be more difficult to do. So it's not something to abuse, but it's something that is super useful. Final rule already. 10 rules is good. I'm happy they didn't do 100 rules, otherwise this would be a long video. All code must be compiled from the first day of development with all compiler warnings enabled at the compiler's most pedantic setting. All code must compile with this setting without any warnings. All code must be checked daily with at least one, but preferably more than one, state-of-the-art static source code analyzer, and should pass the analysis with zero warnings. Have you ever tried having 0 warnings in Unity? It's not possible. I mean, it's possible if you disable warnings. But, I mean, here we are talking about C, right? So having a no warning policy for such high stakes software makes sense. For game dev, where you depend on, I would think, completely unfeasible, because some things are just out of your control, and things that even are in your control are actually not mission critical. Like, oh, be careful, I don't know, this is not translated. Yeah, whatever. Maybe you know that you are not even using that translation. Whatever. This kind of stuff. I would think that 0 warnings in game development is probably counterproductive. The 10 rule is being used experimentally at GPL in the writing of mission critical software with encouraging results. So this 2006, right? I didn't now research what is the state of using this 20 years after. I'll put the link to this document in the description. All right, thank you very much for watching. Like and subscribe. Now you know how to code with NASA coding standards. So you have one more thing in your toolbox to procrastinate and never ship a game. All right, go work on your game.